Greetings everyone, and welcome to our demo that demonstrates how recursion can be applied to a linked list by walking through several common operations. Before examining the details, it is helpful to recall that recursion is a problem-solving approach where a function works by breaking the task into a smaller version of itself. Each recursive function depends on two key elements: a base case that ends the recursion, and a recursive step that moves the function closer to that base case. Linked lists are well suited for recursion because each node naturally leads to another node, forming a repeating structure that becomes smaller with each recursive call. With that idea in mind, our program will print a list forward, print it in reverse, count its nodes, and compute the sum of its values. Each function demonstrates the same recursive pattern applied to a different task. The program begins the node structure. This structure contains two parts: a value stored in the node and a pointer that links to the next node in the list. This simple design forms a chain of nodes and provides a natural basis for the recursive logic that follows. After the structure, several function prototypes are listed. These prototypes introduce the recursive operations that will be used. One function prints the nodes in forward order. The next prints them in reverse. Another counts the number of nodes. The final function adds the values stored in all nodes. Listing these prototypes at the top gives a clear overview of the tasks the program will perform. The first recursive function prints the list forward. At the beginning of the function, a check determines whether the pointer is null. This check establishes the base case. When the pointer is null, the recursion ends because there are no more nodes left to process. If the pointer is valid, the value stored in the current node is printed. Immediately after that, the function calls itself, passing in the pointer to the next node. This sequence of steps moves through the list from the first node to the last one. The next function prints the list in reverse order. It begins with the same base case, checking for a null pointer. The difference appears in the placement of the print operation. Here, the recursive call occurs first. Only after the recursive call returns does the function print the node's value. This causes the values to appear in reverse order, demonstrating how recursion can rely on its returning phase to reverse the direction of a traversal. Next is the function that counts the number of nodes. Once again, the base case checks for a null pointer, returning 0 when the end of the list is reached. Otherwise, the function returns 1 plus the result of calling itself on the next node. With each return, the function contributes 1 to the total count, building the final number as the recursion unwinds. The summing function follows the same structure. When the pointer is null, 0 is returned. When the pointer is valid, the function returns the node's value added to the sum of the remaining nodes. This recursive structure allows the function to accumulate the total value stored in the list, adding each node's contribution as the recursion completes. In our main, we create a small linked list consisting of 3 nodes. Each node is assigned a value and linked to the next. The program then calls each recursive function in turn. The forward printing routine displays the values in order. The reverse printing routine displays them from last to first. The counting function reports the total number of nodes. And finally, the summing function provides the combined value of all nodes. In our demo, although the tasks differ, each recursive function is built on the same foundation: a clearly defined base case, followed by a recursive call that processes a smaller piece of the list. Recognizing this consistent pattern is essential for understanding how recursion works with linked structures and prepares you for more advanced recursive algorithms later in the course. Thanks for following along. We will see you in the next video. Cheers.